אחר צהריים טובים לכולם. My name is Ateret Anaby Tavor, and I manage a research team in IBM Haifa Research Lab. The area is AI. And my main responsibility focuses on devising the next generation of AI for Watson Assistant. And Watson Assistant is IBM dialogue system product, or a chatbot infrastructure, if you will. And today I'm going to present to you an innovative technology that we also published in AAAI. We presented it months ago in New York. And the purpose of that technology is to augment, bootstrap, improve a text classifier via automatic data via generation. So let's start at the beginning. What is a dialogue system? So a dialogue system actually is a system that has an interactive interface. The interface is through conversation. It's conversational. And we in IBM are mainly concerned with dialogue systems that are goal-oriented or task-oriented. So these virtual assistants, they function often within customer care domain ecosystem, and they need to solve a task to help the user resolve some task that they have in mind. So the system, for example, the user starts with saying that they cannot log into the system, right? The system comprises of two components. First, the NLU part. This part is responsible for making sense of what the user just said. This is the example is for one interaction only. Of course, the conversation goes on and on. The interpretation of what the utterance of the user was is by actually understanding what is the intent of the user. That signals to the second part, the more often than not, rule-based system or execution graph that needs to take the signal to the right process. So here, the response is, what is the error code, right? What else? In my team, we are interested in innovative on both parts of the system. Today, I'm going to focus on the first part, on the classifier, the text classifier of the dialogue system. So, targeting the text, the intent classifier? Text classification basically is a supervised learning problem over textual data. So at runtime, the user says something, and users in runtime can say many things and in many forms, and the classifier needs to approximate the right intent. If the classifier doesn't allocate or associate the right intent, the bot will fail miserably. So these systems, in order to approximate and anticipate what is going to be said in runtime, they are highly dependent on the training time. Training time, in order to train the system and to provide enough data to the system, subject matter experts need to work intensively, right? They need to anticipate what is going to be said in runtime, provide enough sentences, such sentences for each intent. And these systems in runtime, I can tell you from a wide and extensive experience, they have 200 intents, you know, in the big customer care call centers. So imagine to yourself, 200 intents. We want to provide for each intent enough samples, and these should be diverse enough, and they should distinguish between, so the samples should relate to the intent, and they can be distinguished from one intent to another. Very laborious. And what we propose is to automate the system. Can we do it? That's the question. And before I show you how we do it, I want to present a paradox. So I'm going to offer a solution that uses generative means in order to improve a discriminative problem. Now, the discriminative problem, you know, the classifier, what it does, it needs to discriminate, to label the sentence when it comes in runtime, right? So the discriminative problem is known to be much, much more easy than the generative problem. What is more easy? What is easier, to create a sentence or to label it? What is easier, to say whether a piece of music belongs to this playlist, to the classic playlist, or to the Kulthum playlist, or to create such a piece? Of course, to generate should have been more difficult. So, am I suggesting to solve the classification problem with a much difficult problem? Well, not exactly, or better yet, not anymore, because now we have a mechanism that is called transformer, which is a game changer in the world of NLP. So transformers are now the state of the art in NLP development, and at the core of the transformer lies a mechanism called self-attention, and they can be found in GPT. This belongs to OpenAI and Google BERT. So here we see GPT. GPT stands for generative pre-trained, and indeed its main characteristic, the transformer's main characteristic, main attribute, is that it's a neural network model which is pre-trained on huge bodies of text. So we were able to utilize GPT in a way that it is not only generated sentences which are sensible, which are appropriate in English, which are coherent, but they were also relevant to the domain. How we did it, how this transfer learning is something that I'm going to talk about in a minute. I want to note that GPT was able to catch the structure of the sentence that we wanted. So if we wanted a question, it caught on this goal of us. If the people in that domain spoke in a specific jargon, then we got this as well in the generated sentences. I'll show you the trick in a minute, how we got it. So our system is called Lambda. Lambda stands for Language Model-Based Data Augmentation. And at the heart of Lambda, we have two innovations, two main processes. First is the generation. We already touched on GPT, right? So what we did is as follows. We took a very small seed data set. What we asked the users is to give us scarce data classifier that has small number of samples for each intent. Imagine five samples, 5 sentences for each intent. This is not enough. However, this is not a big deal for the subject matter expert to create. And what we did is we fine-tuned GPT with that seed data. I will in a minute show you how exactly we fine-tuned it. But this is important that that was the structure of the seed data set, of the training set. And then we generated sentences for each class. Many sentences generated for label. So at the end of the generation process, we have a huge corpus with weakly labeled sentences. Now, what we did with it is we took the classifier that we want to improve. We trained it on the seed data set, and then we use it as a scorer, a double voter on these weakly labeled huge corpus. So for each sentence, if the scorer and the generator agreed on the label, we took the sentence. If there was a disagreement, we deleted the sentence, we removed the sentence from the corpus. And that corpus became the high quality generated corpus that we took to the next level to train the classifier. In a minute, I'm going to show you very nice results that we achieved with this method. But first, I want to zoom into GPT fine-tuning because this is very important if you want to do it yourself. So you can see the trick here. It was to train GPT on tuples of label and sentence. So the label is part of the language model. We sampled equal size intervals of this data set, and GPT understood by that actually the association between the label and the sentence, so that when we gave it in generation time the label, it just gave it a relevant sentence, relevant to the label. Okay. How did we evaluate? We want to improve a classifier, right? And we have a classifier, right? So we took the base classifier, the one that was trained on the seed labeled data set. We trained the classifier also, another classifier, same classifier, on the augmented data. And then we took a test data set and we actually compared them, compared their performance, and looked at the results, and I'll show you the results. But before that, I want to give you a glimpse into how such a generated data it looks like. So here you can see it. I will talk about the 80s data set in a minute. This is data set that has to do with airline and travel information system. What you see here are the sentences, and I want to mention two main things here. First is that GPT gave us the common knowledge, the diversity, and that came from its attribute of being pre-trained on huge bodies of text, right? So the diversity and the common knowledge came from GPT. The transfer learning, the relevancy to the domain came from this labeled fine-tuning that we saw before. Next. Let's look at some results. Before I show you the numbers, I want to introduce the data sets that we used in the paper. So 3 data sets here today for the results that I'm showing today. 2 of them, the top 2 are public data sets that were published with test data that we used. The first one is the Airline and Travel Information System. It comprises all kinds of queries that relate to flight reservation and their labels. TREC stands for text retrieval conference data. It comprises open domain questions with labels. And WVA stands for Watson Virtual Agent. And Watson Virtual Agent comprises of telco, customer supports, intent, and sentences labeled. All right. We wanted to show that Lambda is not dependent on the classifier at hand. Therefore, we used 3 different classification methods. The first one is the support vector machine, very widespread classification method. We have it out of the box of Watson Assistant, from Watson Assistant. That's the Watson Assistant classifier. LSTM classifier, deep learning model for sequential data. And cutting edge BERT, transformer-based model. And BERT achieves state-of-the-art performance on several classification tasks, and the question is whether we can also even improve BERT. So can we? Yes, we can. Here are the results, some of the results. You can see here the comparison of Lambda approach with the baseline. And the data set here is 80s. We'll see the other data sets in a minute. I hope we'll have time. So what we did here, we took the base classifier. Remember, we have 3 different classifiers and a seed data set. So the seed can start from 5 samples per class, 10 samples per class, 20, 50, to 100. And we generated and purified, and then we augmented each class with 100 samples per class. And we tested the performance of the classifiers. You can see the 3 classifiers here. Lambda is designated with a solid line. The base classifier is designated with a dashed line. And we clearly see that Lambda was able to statistically significant improve the classifiers that were the starting point of these classifiers was a small data set to begin with. Look at the 5 samples per class, 10 samples per class, very nice improvement. For all the classification methods, it becomes less and less relevant with the number of samples that come with the classifier as seed, as starting point. And this is not surprising because we are trying to. If I close it here, nothing happens. Great. So. Not surprising, we wanted to augment classifiers that are scarce in data, right? What else? We were able to even augment and improve BERT. That was surprising, but we were able, and you see the result here. BERT is dominant over all the other classifiers for all the number of samples as a starting point. Very significant in the scarce data classifiers, but yet Lambda was able to very nicely improve BERT.
Accuracy here, is it correctly identifying the intent?
Yeah, the accuracy means that when we do have a test data, that we test with all the classifiers, and yes, the accuracy means the percentage to which it identified the intents average over all the classes of the set of the workspace. Okay, so it's an average accuracy.
If you start with 5 samples, how many samples does Lambda
So here, the results that you see here are 100 samples, purified samples, after the Lambda process. 100 samples per class. If you start with 100, you augment to 100. You start with 10. You always add 100. Okay?
100 or you have 100 in the final?
No, you add 100. You add 100, okay? All right. Well, let's look at some more results, and then I'll try to leave a few minutes to questions. So a juxtaposition of all the data sets and with all the classification methods. And we want to show that Lambda does better than other augmentation methods, right? Because there are other generation methods. So the easy data augmentation is something that is well known. Conditional variational autoencoder, we have a lot of experience with variational autoencoders, conditional BERT, and Lambda. And you can see that for across all the data sets and all the classification methods, these are very, very nice, statistically significant results for Lambda. Lambda outperforms all these generation methods. In TREC, it is indeed on par with EDA on SVM and on par with CBERT on LSTM. I don't have time to get into these reasons, but I will mention it because it's important for all the generation tasks, and specifically something that we saw here. So GPT generates for a label. So we really saw that the label and the information that the label holds was important for GPT to understand the domain. And if the label was less informative, then the generation was, the transfer learning was tougher. And this is why here EDA and conditional variational autoencoder were, on par with Lambda. Next, all right, this is something nice. This is an illustration of the magic that we do here with the scorer. I want to show you this one because it really help you with an intuition of what is going on here. But the illustration here is iterative, and Lambda, the results that you saw before, is for one iteration only. So the results that we reported in the paper were for one iteration. Now we experiment in the lab with iteratively, employing Lambda again and again and again. And the way is as follows. Suppose we have a classifier, and it is, as we said, very scarcely populated. 3 examples per class, and accuracy is not so good, and we generate. We generate, and remember, we consult the classifier for the agreement. And the 2 red samples that you see here, one of them, that one on the top, classifier thought it belongs to the right-hand side class. GPT thought it should belong to the left-hand side class. Same goes with the sample over here. So they disagree. Since they disagree, we remove the samples, we train, and we get a better accuracy. We generate again. There is a disagreement on 2 samples. One was on the border, and one belonged, the classifier thought it should belong to the right-hand side, so we remove them, and we train, and the classifier gets better, and we do it again, and we remove, and we train, and the classifier gets better. Okay? And again, and gets better, and that's the idea. So let me emphasize on the idea. For generated sample, even though the classifier labeled it correctly, and we consulted with the classifier before we added that sample to the training set of the classifier, the classifier got better after we added that sentence to the classifier.
But doesn't it create a certain bias?
No, it doesn't. we can discuss it. It really not so intuitive, especially for data scientists. How come we consult with the classifier but the results, you saw the results. Different classifiers, different data sets, and we see it on and again. Scores, we now experiment with other scores. So it's not necessarily needs to be the same classifier. Okay, can be assembles of classifier, etc., etc. But the main idea is this. Let me wrap up. So in summary, we talked about dialogue systems and our mission to bootstrap, streamline their creation, and more specifically, in Lambada's case, we touched on the ability to improve the classifier. We talked about deep learning for natural language understanding and natural language generation, which is advancing super fast, and the amazing, unprecedented results that we saw when we worked with GPT. We talked about the label, which needs to be part of the training, fine-tuning the language model of GPT. And we talked about Lambada, which uses these techniques and showed us, demonstrated that it statistically improved classifier accuracy in scarce data situations and beats the state-of-the-art data augmentation methods. So we can safely say now that improving a discrimination task using a generation is not a paradox anymore.